Thanks very much. Thanks to you all for being here in this session. So today I would like to speak about the holographic entropy cone, which is a construction or a subject sort of right at the interface between quantum gravity and quantum information theory. And so as I said, this is joint work with Sepehr, Nezami, James Sully at Stanford, and Ning, who's in the first row, Hirosi, Ooguri, and Bogdan at Caltech. So the subject, sort of the broad setup of the story that I want to tell today is holography, is the gauge gravity corresponds in high energy physics. And so I guess Patrick gave this beautiful plenary talk on Tuesday, and I just wanted to remind you of a couple of aspects that he already introduced then. So basically the idea is, the idea in holography is that, so the setup is some space-time, so say d plus dimensional space-time like over here, where say this is the time direction and the planar directions are the spatial directions. This particular geometry would be say ADS3, whatever that is. And so the idea is that in the bulks, in the interior of the space-time, there's a certain quantum field theory, a certain theory. It turns out a d plus one dimensional theory of quantum gravity, in fact. And on the boundary of the space-time, so in one dimension lower, there's another quantum field theory. And the statement of holography of this gauge gravity corresponds, ADCFT corresponds in its most concrete instantiation, is that these two theories are dual to each other. So there exists a dictionary that we will not need to go into today that sort of maps states on the boundary, on this boundary theory, to states on the bulk theory, operators to operators, fields to fields, etc., etc. And so I guess there's many dualities in physics. There's high temperature, low temperature dualities. This duality is kind of a strong/weak duality, if you like. So it has the advantage that sort of complicated problems on one side will get mapped to hopefully easier, at least tractable problems on the other side. So for example, this quantum field theory on the boundary could be a theory with many degrees of freedom, a strongly coupled theory, but it would turns out that it would be dual to a semi-classical weakly coupled theory of gravity in the bulk. And so maybe I'll just remind you of these pictures. So as I said, this picture is ADS 2 plus 1, ADS 3. There's one time dimension. These two disk-like directions, they are the spatial directions. And the disk is not a Euclidean disk. It is a hyperbolic disk. And so hence I put these little Escher drawing on top of it, just like Patrick did, so you can sort of associate the two talks. This is sort of zoomed into one of these layers. So into one of these sort of stacks of fish, I guess. And I guess Patrick explained to you this, the significance of the fish, I guess, is if you want to measure distances, you count fish. You just follow a trajectory of fish. Right, so so I thought I should add a little, a slide that is sort of something like an apology, I guess. So why should we care about holography? Why is it interesting in a quantum information theory conference or for a quantum information theorist? Well, I guess there's many reasons. I'll just mention a couple of them. Some of them have already appeared in Patrick's talk. So in a sense, it was observed that by this duality between things on the boundary and things on the bulk, in a sense, entanglement, entropy and entanglement are geometrized, if you like. So we can really, there's certain ways of making this rigorous, and we will see one in just a second, where sort of entanglement between, say, things on the boundary, or between subsystems on the boundary is really explained by the geometry of this bulk theory, and vice versa. So one concrete instantiation is this, is where you see this tensor network that I put on this disk. So Vidal and Evenply proposed this Mera tensor network as an ansatz for, say, ground states of CFT, so ground states of such theories which would live on this boundary. And it turns out that the geometry of this tensor network is precisely a discretized version of this hyperbolic disk. So meaning that this, you could see this as a hint that actually this geometry really plays a role in the entanglement structure. Right? So this tensor network, basically a tensor network is a good tensor network if it sort of reflects these entanglement structures, and it turns out that that's indeed this is the case in these theories. And then in Patrick's talk, he explained that holographic systems share features with quantum error correcting codes. So there was this phenomenon that we could take an operator in the bulk and we could associate this operator to many operators living on this boundary theory. And so the fact that there was this redundancy is precisely the same redundancy that we have in error correcting codes, specifically say Rager codes. There's many further curious properties that people try to explore, and these are properties that probably this community has a very good grasp on things like complexity, gate complexity of states is something that has been of recent interest. And I guess another motivation to study this quantum information theories is that I think there's many ideas that, many concepts that we know that can actually be useful to sort of construct toy models of this AT-received correspondence, which, while well checked, is still a conjectural correspondence. So in Fernando Pastowski's talk, he showed us this beautiful, explicitly solvable, perfect tensor network models, and how it could emulate properties like this. Now, just a couple of minutes ago, I said that somehow this tensor network reflects sort of the entanglement or entropy structure in these states that we consider. So one way to make this precise would be the following. So whenever I have a tensor network that represents a state, I can always bound the entropies of any subsystems, basically by finding a minimal cut with the tensor network. In general, this only gives me an upper bound, but I could sort of think that, if this upper bound is actually pretty close to being saturated, then maybe this tensor network is a good tensor network. It sort of faithfully reflects the entanglement properties of the state. And it turns out that indeed, in this holographic setup, this should be the case. So there's a formula for the entropy of a boundary region due to Ryu and Takayanagi. It's the Ryu-Takayanagi or holographic entropy formula. And it goes as follows. It says, suppose we look at a state on this boundary theory, and we look at a subsystem, say A. And then the statement is that the entropy of A is given by a minimization. It's a minimization of the geometric objects in this disk-like bulk, in this bulk space. And what you minimize over is essentially geodesics, so paths inside this bulk that minimize the distance between, say, this endpoint and that endpoint. More generally, the recipe is that you should look at surfaces that are homologous to this boundary subsystem. But in this case of intervals, this is precisely that. So this is another very strong sense, a very precise sense in which entanglement or entropy is geometrized by this dual theory. And so what I want to do in this talk and what sort of what our work is based on is basically, well, let's take this formula, which is sort of a well-checked proposal that has been proved to various degrees based on ADS-CFT. Let's take this as a definition. Let's study the properties of this function. So what I want to do in the coming, I guess, 15 slides is I want to sort of deconstruct this formula. I want to really sort of understand, is this a geometric formula? I actually want to convince you that this is a very combinatorial object in many ways. And I want to introduce some sort of ideas that we know from quantum information theory to study this entropy formula. And then there will be a number of applications. And there's going to be sort of interesting features that this formula sort of displays, but about things that we don't actually know, say, for the von Neumann entropy, or for more general entropies, or different entropies. All right, so let's get started. So the title of my talk was the holographic entropy cone. The title of our paper was the holographic entropy cone. So what is this object? It's basically, it's sort of the most naive definition that you could do if you wanted to study entropies of a certain number of subsystems. So the idea is, suppose I have n subsystems, A1 to AN. And I want to understand sort of what are all these sort of entropic constraints that are satisfied by an arbitrary collection of n subsystems in an arbitrary, say, quantum state. So then what I could do is I could just take, I could take my state, I could compute the entropy of the first subsystem, A1, the entropy of A2, and so on, the entropy of, say, the first two subsystems, and so on and so forth, up until the entropy of the union of all the subsystems together. This would give me a gigantic vector of 2 to the n minus 1 elements. And now I could vary all the subsystems, and I could vary over states. In the context of this holographic entropy, what I should instead do is I should vary over all geometries. So not only look, say, at this hyperbolic disk, but say arbitrary geometries. Maybe I want to impose constraint on those, maybe I don't. And as well as over arbitrary subsystems, or in my case, boundary regions. So by doing this variation, I get some set, which I could call, say, the entropy region associated with n subsystems. And studying the set is almost by definition equivalent to understanding the entropy, entropic constraints obeyed by n subsystems and their composites. The reason why this is a good definition is that in many instances, in the case of the Shannon entropy, in the case of the von Neumann entropy, and also in the case of this holographic or Ryu-Takayanagi entropy formula, this turns out to be a convex cone, or up to closure to be a convex cone. So this object being a convex cone, what means by definition that if I take a point like here, then there's a natural rescaling operation. So I can take a point, I can take such a collection of 2 to the n minus 1 entropies, and there's a way of basically obtaining another point in the cone, which is just given by rescaling all the coordinates. Likewise, I can take two such vectors and I can add them, and I should still get a point in the cone. In this geometric context, this is quite natural because rescaling basically just amounts to rescaling a length scale. So you just change the metric, hence all areas, all lengths, like lengths of curves just get multiplied. Whereas adding points in the cone corresponds to taking the disjoint union of different geometries and their corresponding boundary regions. So this is in a very clean way, this object is a convex cone. And so now we're happy because we have a convex cone can say be described by linear inequalities, say by facets, as well as say by extreme rays. So the appeal of facets, what are these facets? Here's a little example of such a cone. So one axis is say the entropy of A, the other is the entropy of B. This is the entropy of AB axis. This would be an example for n equals 2. It turns out this is precisely this. It's the holographic entropy cone. It's also the von Neumann entropy cone. And the bounding inequalities, so the facets of this object can be identified with inequalities, and they're precisely the linear inequalities in these entropies. So the significance of this object is that it's basically in one-to-one relation with a set of all linear entropy inequalities that we like to study. Right? So for example, strong subadditivity is one such bounding hyperplane. The Araki-Lieb inequality might be another one, et cetera, et cetera. And the fact that this very region is a convex cone says that it makes sense to look at linear inequalities. Right? So a priori, maybe you would have wanted to look at nonlinear inequalities, quadratic things in the entropies. But because we are bounding such a polyhedral object or such a convex object, it makes sense to look at linear inequalities only. Now, so this is maybe, OK, so mathematically, I guess this is a nice definition. It has some nice structure. It also seems pretty hopeless to work with, right? Because somehow in the definition in here, like it is the set, like, to compute a single point is easy, but we have to vary over all like choices of subregions, all the different geometries, which is some crazy, continuously infinite object. And so it might be nice to actually cut down this complexity in some finitary and obtain some finitary characterization. And so this is what we did next. And so the idea was basically the following. Suppose we have this particular geometry. So I will always, basically in my, in all my talk, there will be basically these little Escher disks, these little Poincare disks. So suppose I have, again, this geometry with a circular boundary and three regions like this, A, B, and C. Now, the entropy associated to the subregion A would be given by the length of, say, this red arc. The entropy, say, of AB would be equal to, as usual, the entropy of the complement. The entropy of C would be equal to the length of this arc, et cetera, et cetera. Now it turns out, as I look at these 2 to the n different subsystems that I can form from A, B, and C, or A1 to AN, in the end, I only look at, I look at a finite number of subsystems. So I can take all these arcs, or more general, all these minimal surfaces, and have them partition this bulk geometry, so this spatial slice. And so, for example, in this simple example, I got 4 chambers. I get this chamber, that chamber, that chamber, and that chamber. So now what I can do is I can define a graph where I associate a vertex with each of these chambers, and I add an edge with a certain weight, and the weight is precisely equal or, say, proportional to the area, say, or the length of this arc over here. And so, quite trivially, from this picture now I have constructed such a graph, such a trivalent star graph in that case, where I can label this piece by A, this vertex by B, and that vertex by C. And by construction, it is now true that this Ryu-Takenagi entropy formula in this continuous geometry agrees precisely with the weight of a min cut in this right-hand side graph. For example, to compute the sort of combinatorial entropy of this vertex A, there's basically 2 cuts that I may consider. I can cut the graph like that or like that. And when I minimize, I find this is the min cut. But by definition, the weight of this edge was defined to be the length of this curve. The crucial point now is that you can also go the other way. So I can take an arbitrary graph like that, an arbitrary weighted graph. And from this weighted graph, I can construct a geometry, actually a hyperbolic geometry. And the Ryu-Takenagi formula in this geometry that I constructed will be precisely equal to the weight of a min cut. So the upshot then is that actually looking at graphs is precisely equivalent to look at continuous geometries. And so in this way, we have sort of brought down the complexity of studying this entropy cone. We can now characterize this entropy cone precisely only by looking at such graphs. Yeah, I guess I will comment on a bit more later on how we go back from these graphs to continuous geometries and how we actually obtain.
Can the graph be arbitrary?
In principle, the graph can be arbitrary. So we do some graph rewriting to sort of bring it to a nice normal form, and then we can do something like a pair of pens decomposition, and we can build a nice, say, hyperbolic geometry from it. In principle, it can be arbitrary. So here's so in the remainder of my talk, I want to spend basically, I want to spend the remainder of my talk discussing some applications of these, basic constructions. So the first observation basically that we have is that it turns out that this cone is polyhedral, so this entropy cone that I defined before. And so this might seem like a very technical statement, right? So what does polyhedral mean? Polyhedral says that the cone it's not a roundish cone, like it doesn't have round aspects, right? It's a cone that has finitely many faces, and equivalently finitely many extreme rays. It's a cone that looks like that, just a bit a tad more complicated in general, and so the reason why this is interesting is because it basically says that studying this cone, to describe this cone, we only need a finite number of entropy inequalities. So for each number of subsystems that we care about in this holographic context, there exists only a finite number of linear, holographic entropy inequalities that we need to consider. So there's actually some hope to actually figuring out precisely what these cones are for each finite n. Of course, as you increase n, the number of subsystems, this object will increase in complexity. And so maybe it will not be tractable to do so for an arbitrary n. But in principle, there's a finite answer. And the way by which we prove is it really relies on these graphs that I presented earlier, because we can sort of strengthen our this graph description over there, and we can actually put an upper bound on the number of vertices in these graphs. So in principle, I was saying that we can look at arbitrary graphs, but we can always actually simplify them by a procedure that's very much like the one I did here in the continuous case, down to a bounded number of a doubly exponential, but a bounded number of vertices. And this then readily implies that everything is sort of linear programming-esque, and hence things are like finite and polyhedral. It is interesting to point out that this is actually an incorrect statement for the Shannon entropy. So for the Shannon entropy, you can make similar statements. You can make a similar definition. You can construct such an entropy cone where S now means the Shannon entropy. But in that case, the closure actually, we know that it has sort of round features. And it's an open question for the von Neumann entropy, an interesting open question. So I guess it's another hint that these holographic entropies are much more special and sort of well-behaved. A second application, which is maybe the main application that we have in our paper, is that this combinatorial point of view gives us allows us to prove entropy inequalities, entropy inequalities for this Ryu-Takanagi formula in a very combinatorial way. And so before I describe to you our method, let me sort of describe to you a previous method that Hedrick and Takanagi used. So when Ryu and Takanagi came up with this entropy formula, it was a proposal. And it was not clear that it should be correct. So what they did, they did many sort of sanity checks. So the proposal was that a certain von Neumann entropy is equal to this geometric quantity. Now, von Neumann entropies satisfy laws like strong subadditivity. So, one natural sanity check was to check that actually this geometric prescription that we took as the definition in this talk satisfies strong subadditivity. And the proof is really very, it seems very simple and it's very beautiful. So let's just illustrate this in a certain example. So here I changed coordinates a little bit. So the boundary now is this line. It's no longer a circle. You could think of it's like a piece of the circle, and this goes out to infinity. And this upper half plane is now the hyperbolic half plane. This is the hyperbolic half plane model rather than the hyperbolic disk. So the bulk goes upwards, and this is the boundary direction. So let's take three subsystems, A, B, and C. The entropy of AB would correspond to the length of a minimal curve, say this curve over here. The entropy of BC would correspond to the length of that curve over there. And now we want to prove this entropy inequality. So we want to prove that the sum of the lengths of these two curves is lower bounded by this right-hand side. And so what we'll do is what Hedrick and